Hi everyone, so my name is Matt, I'm from Ocado, more specifically Ocado Technology, which I brought my jeans and my beard to prove to you. I'm going to talk to you a little bit about how we use a lot of the techniques you're hearing about today to do what we do. So who are we? Hopefully a few people in the room know who Ocado are. World's largest dedicated online grocery retailer, hundreds of thousands of shoppers all over the UK. Wider range than any supermarket that you can physically step into. And we can do all of that because we ship from large centralized distribution centers, and we have a lot of automation and robotics inside those sheds. So nowadays, on top of what we do in the UK, we're also helping to put the world's grocery retailers online with the intersection of several different technologies, all of which is underpinned by modeling. So we'll start with what we did a little while ago. We used to build systems that look like this. We would have sort of 17 kilometers of conveyors, crane systems, shuttle systems, all stitched together and moving around inside a big shed. These we now call legacy systems, but they are still the most advanced of their kind in the world. The two that we have in Hatfield and Dordon, they ship upwards of 350,000 orders per week around the UK, which means that each of those warehouses can pick and place about 1.5 million individual items in a shift. So these are big, big, complex machines. And when we started building them, our modeling tooling looked something like this. So it was fairly basic, to say the least. And as we started to scale these systems and learn a bit more about the technology, it became clear that we needed to actually go out and do something a bit more seriously. So we started to build a model of what we actually had. And eventually, we ended up with something that looked a little bit like this. So this is a layout of one of our conveyor-based CFCs, Customer Fulfillment Center, for those who don't know our jargon. What we actually have is a set of connections at the back which lets you access these various pick aisles. And we would send your little box with your bags down one of these aisles, and it would queue up and enter various stations where a human picker would take some strawberries or some bread or whatever it is and put it in your box. So your box or boxes will go on a journey around the aisles they need to visit and eventually end up in a buffer here where we put everything on a van and ship it to you. So we have different temperature regimes. You've got your ambient and chill, and then you've got the sort of output of the system in blue. Now, to build this model, we spent a lot of time wandering around our warehouse with stopwatches and looking at sort of paper CAD diagrams and various bits and pieces to build the actual digitization of what we'd already built, because we came to this after the fact. So there was a lot of work involved in putting a model together originally that allowed us to test new layouts or test new algorithms. But eventually we built that, and we ended up with something that looks like this. So this is a software called Mimir, and you can now actually look at what the system's going to do. You can modify the topology of your conveyor, try out new layouts, see what tactical upgrades you can put in to get higher throughput. And you can then simulate customer orders. So we will take customer orders that we've actually data mined from previous days, and we'll run them through the site and see how they perform. And then you have the analytics layer on top of this that you can use to understand the system. So for example, what you see here, we have a red aisle because that buffer is full, and that's where we have the risk that one of your boxes can't go in the station at once, so we have to miss it and come back and queue again. And as those effects propagate through the system, you get congestion and you start to introduce delays. We can also track your box all the way around the warehouse and see it as it goes on its little journey. So eventually, we ended up with what we now call a digital twin, which is not a simple model, but something that actually covers everything inside the shed and lets us completely test new ideas, new layouts, figure out what we should build next, what it's going to be worth, when we would need it, We can have a look at what we're going to sell this Christmas, which is the biggest day for us. It has a very different profile of what people buy at Christmas. Buy a lot more turkey in December than you do in sort of April. And we can plan ahead and figure out which projects we need to have ready. So that's what we did then. What we do now is something that looks a little bit different. So this is our new smart platform. Again, there's been some press about this, so you may have seen this before. But essentially, we have some bots that move around on a grid, and we've got some boxes under that grid. And we stack them, which allows us to get very, very dense storage in 3 dimensions. So I can sort of play that through for you and give a little bit of a visual cue. Some nice modeling in CAD. There's a crash bar around the outside. You've got X, Y motion on this grid, and you've got bins stacked up. These bots are then centrally routed. So there is an AI system that's talking to these machines and choreographing all of their motion. So they have this winch system. It lifts up a box inside. They move somewhere else, and they put the box down. They're either storing it somewhere that we need it stored, or they're putting it into one of our peripheral machines, which is something like a pick station, for example, or a human operator can then take the product and put it into your bag. So within this one system, which we call a hive, there are lots and lots of processes going on. So in the conveyor warehouses that I showed before, we kind of had a patchwork quilt of different things happening. So we would have an inbound process where a pallet would come in and we would split the pallet, and then a crane would go and move things around and stock the aisles. We'd have some AI that would decide the optimal place to put different SKUs in the aisles. So the strawberries are more efficient here than here. And then we'd have the conveyor system I showed you, which is the outbound process. So there were lots of different machines all working in tandem. What this setup does is it puts everything together. So the only complex moving part in this machine is the bot, and it's completely redundant. So if one of them has an issue, you kick it off the grid and put another one in, it does the same job. Now, what you're seeing here is an example of some of the main processes that are going on. So the pick process is the most important one. That's your stuff going in your bag. And as I say, we take stock over to a pick station, and we put things in your bag, and then we complete your little box. Your box goes back in the grid. So the buffering and aggregating of routes ready to go out into the logistics network is also done in the hive. The new stock coming in from suppliers is the inbound process in the top left. We do all of that and we put it in the hive. We've got the empty stuff after we've delivered. We get a box back, we put that in the hive, and everything is managed in the central system. But to do that efficiently, you need to have an enormous amount of processing and algorithmic complexity. And you cannot build something like that without a model. So one other thing to mention is the bot itself. That's a complex machine too. There's 10 subsystems inside it. You've got your XY motion, the hoist system, the battery, the change of direction mechanism, and they all generate huge amounts of data. They need careful management. These things travel at 4 meters per second. They communicate with our central control system 10 times a second, and they pass with a 5 millimeter clearance in between them. So the actual choreography of how you move these things around is very important, and again, it is impossible to create a system like this without modeling and the digital twin that I will show you in a bit more detail. So one thing our twin can tell us, by the way, our site in Erith, we can look into the future with that site, and when it's fully ramped up, we already know how many orders it's going to ship because our twin told us and we trust it. And the bots on that grid will travel in 24 hours about 180,000 kilometers in aggregate over the fleet, which is just under 4.5 times around the world. So there's a lot of motion and a lot of control going on in this system. So this is what it actually looks like. This is drone footage from inside our warehouse. We actually had to fly the drone through about a 60 centimeter clearance between the bots and the various things hanging from the roof to get this footage, but it gives you an idea of the speed, the density. We can see the white boxes down here with all the products inside. And to make this possible, we have the model, which I will now show you, or I'll let this play because it's nice to look at. There we go. So this is the model. This is what we actually work with to develop our algorithms. We've got a full site grid here. This little guy's a bot. There's lots of them. They're all coloured based on the process that they're performing. So the guys involved in the pick process are in green. These light green ones are bringing stock to pick stations. They're running along the centre here. Dark green is putting that stock away again. All the other processes are there. You can see how much stuff is going on at the same time. Now, I'm going to make these move in a second, but I will first try to describe what you're about to see, because it's a bit complex and a bit nerdy. I love it. I don't know how many other people will be into it. Make it move. Okay, we'll do it while it happens. So, no, we're not going to do that. We're going to do that. There we go. So the guys move around. Inside the brain of the system, this is the path planning engine. So we've got time going up the z-axis on this video, which means the higher up something is, the further into the future you are looking in the plan. So everything should be at a slight gradient, and that's basically where the bots are going to go. When it reaches the grid, that's now, and you can watch a bot follow its path through here. You will also see new bits of plan being added all the time, and this is the real-time management of that process. So every time something asynchronous happens that we can't control mechanically, we'll update the plan. And the most common thing that happens is one of our human pick operators will press a button to say they've finished putting the bread in your bag. We don't know exactly how long that's going to take, so we can't plan the machine around it. So as soon as we get the notification from them, we'll put a new plan in to go and pick up that box and put it in the other processes. This is what you would actually see if you were a picker. So boxes of stock are arriving on the green conveyor. They're being dropped off by our bots into these two positions, and we're taking stuff out of the pick position and putting it into your bag, which arrives in the red conveyor. So this is sort of showing the pick process. I'll link us on this a little bit too long, but it will go back to the cool stuff in a second. The whole thing allows us to do a host of activities. It allows us to impress rooms of people with videos. We can develop our algorithms against this system. In fact, the algorithm that's running here is the production algorithm. It's the same thing. We don't have any difference between what we run in our warehouses and what runs in our simulation. We can optimize the layout of our site. And it was a good point earlier that optimization and simulation are not the same. The simulation enables us to try different layouts and see what works. We can test the software itself against this system. Because the production software runs here, we don't need to debug as much in production. We can debug things against the simulation first. We can visualize system performance. So we can get an intuitive view of how things are happening, and we can also have an analytical view where we actually have a scripting layer on top of this software that we've developed that lets us color things in based on what's going on. So obviously you're seeing the task-based stuff here, but we can have all kinds of coloring analytical schemes. We can play back the live feed of data from our warehouse through this same software. It looks very similar because it's the same software making the decisions. We can also do historical postmortems on stuff that went wrong. So if we had a bad day and we're trying to figure out why, perhaps there was something complex in the orders for that day, perhaps we hadn't anticipated something, we can take the stream of data, play it back through here and see what was going on. We can go halfway through that day, change some config and simulate from that point to see whether that would have saved the day if we'd done it in time. So there's an operational training aspect to it as well. We can forecast against known periods, such as Christmas, and we can also look at the impact of new technologies or hardware improvements. So we can look at the precise operational gain if those bots moved 5% faster or accelerated 5% harder. We can start to weigh up the engineering project cost against the actual delivery of the site and what we're going to get out of it. So that's our twin. I'm I'm very proud of it because this is something I've worked on. We have a little bit of insight into this now because we've done it twice and we did it differently the 2 times. So the first thing that we've learned, or in fact the first thing I'll say, building or growing the twin, what do I mean by that? The definition of a digital twin is kind of a new phrase. I think there's maybe some people think different things. For me, twins are born together, and we've had a very different experience, the thing that we've grown alongside the product compared to the thing that we had to come and retrofit. So that early start was a massive, massive win in terms of where you could get to and how quickly that product developed and what it was capable of in the end. So it's really important to start modeling as early as possible. I also agree with Suzanne that it's certainly not too late to start if you haven't yet. We, again, have done both. The first time was definitely worth it, but it was a lot more manual. It took a lot more work. And, of course, you see the benefit later. And you may have made different decisions that you could have improved on if you had the model earlier in the process. The twin only needs to be as complex as the product. So we actually have 2 simulations that we use for testing this big grid system because there is a boundary condition. So down to the point where you speak across the wireless interface with the bot, the AI system is kind of in control of that whole process. It tells the bot what to do. We don't need to model the physics of the wheel on the track in order to improve on that system because we can't talk to it. There's a boundary there. So we can only give it this small set of commands. So there's no point going any further. But we do model everything else underneath. It's just a separate simulation. And it's hugely simplified by decoupling those things. So it's not necessary to have every possible aspect of your model all in one go. You can always find good ways to abstract and good ways to get value out of something without needing to add unnecessary complexity. Parallel development to drive your design. So this is the whole thing about the twin being born with the product. We started developing the bot and the bin and the grid on day 1 and the simulation effectively at the same time. So every time we learned something in simulation about the most efficient way to run something like this, we could feed that into the engineering process. So we may find that it's so important to get the acceleration of the bot up. You need to choose a new motor. This is really, really worth it, even though it seems hard or expensive now, it pays off. And likewise, every time we think about the real operational requirements, how the people are going to be manned and managed, how you can get engineering access and maintenance, you feed that back into the models that you're simulating to make sure it's realistic. So there's a real sort of synergy there between the 2 processes when you start them on day 1. And the last thing that's certainly been a really important learning for us is that your twin, if you invest in it, will tell you things you didn't know you need to know. So we built the simulation to develop the control algorithm. So I'm a software nerd, that's kind of what I do. But quite late into the process, we used it for all kinds of stuff. So we can ask our simulation, well, if I know where every bot's going, I know when they exert lateral forces on the grid because of acceleration, deceleration. And I can use that to determine the fatigue on the grid with our friends at Arup, in fact. So we've done all sorts of studies on the physicality, the engineering, all kinds of things, which were certainly not in the brief for the product and would have been almost impossible to do accurately without this. And they all came later. So there will be secondary benefits that are, it's just worth doing. It's great. So a special mention to determinism and discrete event simulation. That's the actual type of modeling that I was just showing you. Determinism is great for software development because it gives you loads of cool techie stuff, which my colleague Gareth will be able to talk about in any detail you like in the panel later. I probably don't want to do a deep dive into the software side now, given it's a short talk, but the coolest thing is time machine debug, by the way. If your software is perfectly deterministic, you can replay it identically the second time. So if you have a bug that happens way into your simulation, you can almost perfectly reproduce it and pause on a breakpoint. It's fabulous. So we use a lot of discrete event simulation at Ocado. It's one of our very precious core competencies. I can't recommend it highly enough. So that's how we do what we do. It is certainly worth doing this, particularly if you deal with things that move, but more generally, things that change over time, of course, which is roughly the same problem. And lastly, I'll talk a little bit about what we see as coming next from us. So we've had a vision for a long time of changing the way the world shops, but that's more as a retailer, and again, I'm from technology, so we have a slight variant on that, which is this slightly bolder statement. But there's an important point perhaps for this audience, and certainly in this room, which is that if we want to improve productivity in the UK, and we want to be a leader in things like autonomous vehicles and smart cities, then we need to accelerate our learning. And the way that we have managed to do that has been through these modeling processes. So there's a couple of ways you can do that. One is through living labs. So if you look at Cyborg Labs in Toronto and this kind of thing, you can do this parallel development type process. So you are building your model of the various systems at play in your city, and you're getting constant feedback from the ways you can use these things. And that is incredibly valuable. I encourage you to go and have a look at what those guys are doing. It's hugely exciting. And there's also a wider goal of perhaps building a digital twin of the entire UK and all of the systems and processes at place, and the possibility of crowdsourcing the information that goes into that. And that's something that we're starting to think about, and we're very excited to see what we can do there. We're certainly very interested in a relationship with Bays for that, and watch this space, I guess. Fantastic. Right, thank you very much.